What number lab is this? 4?
5.
5? Okay. Calorimetry. On 13 October. Okay. So overall, what are we trying to accomplish with this exercise? We're trying to determine the measuring heat, calorimetry, measuring heat. We're going to measure the heat transferred, produced or absorbed in various processes. In fact, we've got 3 processes. We're going to acid-base reaction. We've got 2 heats of solution. One is sodium carbonate in water. It's temperature balanced. It does that. But before we do that, we have to compensate for the calorimeter, because the calorimeter will introduce either absorption of heat or release of heat in a reaction. So we've got, that's why the boiling water. So the first step is in this page on determine the calorimeter constant. That's what that's all about. Okay, before we get to that, let's look at these pre-lab questions. Let's see, 1, pre-lab. One mole of acid and 1 mole of a base react to form 1 mole of water in a neutralization reaction. 1 mole of acid. Doesn't tell you what the acid is. Just so we have to say something like this: 1 mole of acid plus 1 mole of base produces 1 mole of water. Well, that only accounts for the hydrogens and the oxygen. So what we got left over is the salt. This cation plus this anion. Okay. Okay. So if this is true, if this is the stoichiometric ratio, why do we use an excess of sulfuric acid in this procedure? We use an excess H2SO4. So why is that? I'm sorry? You're warm. Remember what I said? Well, actually, not in this class. It would have been in the.
Is it like?
Yeah, in this class. Right.
Is it like the amount of molars that the acid is? Is it like concentrate?
No, actually, we're adding 0.5 molar H2SO4 and 1 molar sodium hydroxide. So that imbalance is taken into account, where this one has 2 protons produced and this one only has 1 hydroxyl.
So that's not the answer.
No. It has to do with stoichiometry itself. Remember, theoretically, a stoichiometric mixture is exactly equal amounts of the hydrogens and hydroxyls. So we would use half a volume of this to a full volume of that to give you a stoichiometric mixture. Well, let's write out the actual equation. Right, if we got H2SO4 in aqueous solution and sodium hydroxide in aqueous solution, then that's going to yield sodium sulfate We need two sodiums there because sulfate's 2 minus. And then water. Okay, so let's balance the equation. We need 2 sodiums. Right? And that gives us 4 hydrogens and 2 oxygens. So 4 hydrogens and 2 oxygens. So that's balanced. Okay, a stoichiometric mixture would be twice as many moles of sodium hydroxide as moles of sulfuric acid. So if this is already 1.0 molar and this is a half molar, then we've taken into account the difference in this stoichiometry. So if we use equal volumes, what was it, 25 mils each? Or is it 75 each? No, it's 50 and 60, right? Okay, if we were to use 50 each, that would be a stoichiometric mixture. Right, because 50 mils of this would produce a certain, well, actually, let's do it. This would be 25 millimoles of H2SO4, which would be what? It would be 50 millimoles of hydrogen ions. Did I explain millimoles before? Okay. Molarity times milliliters is millimoles. That way I don't have to bother changing this to liters. So that's 50 millimoles of hydrogen ions from that 50 milliliters. 50 milliliters of this is 50 millimoles of OH minus. Okay. So we get equal amounts here. And that satisfies the net ionic equation for an acid-base reaction. Right, equal amounts. So 50 millimoles here, 50 millimoles there. All right. So in this case, 50 milliliters of each would be stoichiometric. Would be the perfect balance. Okay. I said all of that to say this. That will never happen. No matter how much you try, you will never get exactly a stoichiometric mixture. It's just, there's too much error involved.
It's because of like yield or something. Kind of.
Warm. It's not really the yield. It's
Like
limiting.
reactions are never like, they're never perfect. And that's like if it's perfect.
I see where you're going. No, that's a different topic. This relates to the fact that since we can't guarantee that we have exactly 50.00000 millimoles of each one, so that we have a stoichiometric mixture, we use excess and limiting. So the limiting is going to be sodium hydroxide because we actually have 60 milliliters of this one. So this one's limiting, and when that one runs out, the reaction stops. That guarantees that all of this is used up, and it uses up 50 millimoles of this one in the process, and it has some left over. Okay, so we're not concerned with the excess hydrogen ions in this case because we're only interested in the heat. So the heat that's produced is based upon this limiting reactant. Right? That's limiting, and this is excess. Okay? That guarantees that we get a complete reaction. And then when we determine the heat of this reaction, when we get a Q value, and I'll show you how to do that in a few minutes. When you get a Q value for this reaction, it will depend on how much is reacting. Right? If we put 100 milliliters here and 110 here, we get a complete reaction, but there'd be more reacting acids and bases. So that value would be higher. So, and that's an extensive property. We need an intensive property, one that will not change with amount. So we reference it to one of these reactants or products. And the best way to do it is to use this net ion equation and reference it to the moles of water produced. So that's why when you get this Q, then you divide it by the moles of water. And if you look at the last page of your the method, there's a table back there, right here. That gives you accepted values. And the bottom one is the accepted value for this reaction. Right? How much heat is produced per mole of water? Minus 57.9, so it's exothermic reaction. Okay, that's what you compare your value to for the first experiment, acid-base reaction. And that is kilojoules per mole of water. So if your answer comes out in joules, in order to compare it with this one, you need to convert it to kilojoules.
So the answer is like to account for error.
To guarantee a complete reaction. Okay, that was one. Let's see. I mean, we got three pre-labs. Yeah. Let's see what can be gained from two. You're an engineer assigned to choose a material that will protect the spaceship from destructive heat when it re-enters the atmosphere. Your two choices are aluminum or iron. Considering only heat capacity, the molar heat capacities of aluminum and iron are 24.35 and 25.1 respectively. So the heat capacity for the molar heat capacity for iron is, well, they did aluminum first. Heat capacity for aluminum is 24.35. Joules per, is it joules? Yep, joules per degree C mole. And iron is 25.10 joules per degree C mole. Okay, that's given. What's the question? Yes. Which one would provide the best heat protection? Yes. Think about what you're trying to do with your spacecraft when it re-enters.
It's throwing me off because spacecrafts use a lot of aluminum.
Yeah, this is purely hypothetical. In fact,
They're made of mostly aluminum.
In fact, the last spacecraft we had didn't use either one. They used ceramic bricks or carbon-carbon, advanced carbon-carbon on the hottest part of the space shuttle, on the leading edges of the tail and the wings, because that withstood a higher temperature. You're trying to protect the internal structure of the machine from those high temperatures. So what you do is you put a material there. Well, actually, there are several ways to protect a spacecraft from heat of reentry. One is with a metal shield that is designed to slough off and carry the heat with it. Those are called ablative heat shields. And that's what was used for the Mercury, Gemini, and Apollo spacecraft. And I think that's what they're going to do with the new Space Launch System. With those capsules, they're going to use ablative heat shields. And then you just design them so that you can take off what's not blown away and just replace it with a new one. Now SpaceX, the Starliner, I think they call it, they're getting ready to test their Starliner with ceramic bricks. They're going the ceramic route. And I think they can do that because the Starliner is made of stainless steel. It will stand up to excess heat a lot better if one of those bricks cracks. And that's up for debate probably. Anyway, back to this one. You want to select the material that will change the least amount of temperature for the same amount of heat. And that's, you can put more heat into this one with less change in temperature. So that's why the higher value is the best. And one last one. Before we actually talk about the lab. The enthalpy of solution of sodium hydroxide is minus 44.5 kilojoules per mole. Enthalpy of solution. So what does that mean? Well, this is a negative value. What was it, 44.5? 44.5 kilojoules per mole. The enthalpy of solution for sodium hydroxide, and I can confirm that, because that is that sodium hydroxide there. Thank you. Yep, I made that up yesterday from solid sodium hydroxide. It took 40 grams in 1 liter.
You guys love.
Oh, thank you.
Sorry.
Mine is that.
Just thought I'd tell you.
Was that thing tripped? It's not charging. Now it's charging. I was just starting on the pre-lab questions. I figured, did I mark my face?
Are you having a day today?
Yeah.
Looks like you did.
It's not my calculator today.
I don't see.
Okay.
It's not super noticeable if you did.
It's not like Police Academy where I put the megaphone in my mouth and I have a black circle on
Yeah. It's definitely not like
it. Okay. So this is the heat of solution of sodium hydroxide. And the solution gets very hot. So I made that actually the day before yesterday and let it sit overnight to cool. And let's see, what else? 10 grams of sodium hydroxide. So mass equals 10 grams of sodium hydroxide dissolved in 75 milliliters of water. The volume is 75 milliliters of water. Okay. At 21.1 degrees. So initial temperature is 21.1 degrees C. What would be the maximum temperature attained? The heat capacity of a calorimeter is 1 times 10 to the 1 joules per. So that's big C. That's just 10 joules per degree C. Did we talk about that during lecture? Okay. The difference between heat capacity and specific heat capacity. I think we did. Heat capacity is an extensive property. In other words, if you have more substance, you'll have a higher heat capacity. But specific heat capacity is independent of the amount of substance because it has ratioed in it. Well, for water, is that what's given? It's not given. So we have to put in a value. 1.184 is the one I've been using. Joules per gram degree C. So that's the amount of heat required to change 1 gram of water 1 degree centigrade or Celsius. My heat capacity, since it changes with the amount, if you have more, the heat capacity will be more. It's on the joules per degree C. Okay. And the calorimeter constant, this big C, is specific for that calorimeter that you construct today. If you change anything in it after you've determined that constant, then all bets are off. You have to redetermine if you change anything. If you change the cups, if you change the lid, if you change the thermometer you've got in there, then that will change the calorimeter constant. But in this hypothetical situation, we're given calorimeter constant of 10 joules per degree C. Okay. So back to the question. What would be the maximum temperature attained? All right. So the maximum temperature is the final temperature. All right. Here's how, and working this problem will actually kill 2 birds with 1 stone. I was intending to discuss what you do with your data. And our isolated system is still going to be 0. 0 joules is equal to all the changes that occur inside the calorimeter. One of those changes is the heat of reaction. And that's just going to be a bare number for our method. And then the other one is going to be the heat of the calorimeter. Well, actually, no. The heat change of the water and the heat change of the calorimeter. So those 3 factors are common to each of your experiments today, all 3 of them. Okay. So let's see. We have enough information to solve this problem. The heat change of the calorimeter, I'm going to have to spread out some, I think. Let's leave this one as is for now. We may expand that one. No, we will have to do this one. We will have to expand this one. So the Q of the reaction is going to be the you got 10 grams of, here's the molar heat capacity for sodium hydroxide in this solution. So that's the total amount of the reaction, kilojoules per mole. Minus 44. And each one of these terms has to resolve to joules, right? Because that's what this 0 means. All the joules cancel out. Right, so if this is minus 44, let's change it to joules, times 10 to the 3rd joules per mole. Well, how many moles do you have? Well, you have 10 grams. So what's the molar mass of sodium hydroxide? You got to change this to moles, right? Sodium is 23 is sodium. Oxygen is 16, and water is 1.01. I mean, hydrogen is 1.01. So that's 40.01. So 10 divided by 40.01, let's just round it off. 1 divided by 4 is a quarter, right? So moles here. All we need is moles. 0.25 moles of sodium hydroxide. Let's see, and the temperature change of water is going to be 4.184 joules per gram degree centigrade. And I'll write it here. Joules per gram degree C times the mass of the water. Where's the mass of the water? 75 milliliters. So this was mass of the sodium hydroxide. And mass of water is 75 grams. So 75 grams here. And then the temperature is final temperature minus initial, 21.1. Okay? And let me move this up here. Okay, so that's the water. Now the calorimeter. The calorimeter introduces a correction factor of 10 joules per degree C. So this big C here, 10 joules per degree C, is multiplied by final temperature minus initial temperature. So it's going to be the same as the water that's in the calorimeter. So there's our formula, and we just solve for TF. Stop me if you have questions. So 44 exponent 3. Let's change the sign on that. And then 0.25 times that. So this term is minus 1.1 times 10 to the 4th joules. This one, let's do this part right here. 4.184 and 75 is 3.138 times 10 squared. And then if we expand this one, we're going to have 3.138 times T to the F minus 3.138 times 10 squared times minus 21.1, which is 6.621 times 10 to the 3rd. Okay, so that's this group here. And this one is 10 TF minus 211. Okay, so far so good. Okay, so let's see. We've got this is a free number. That's a free number, and that's a free number. So we'll combine these three. So let's see. This one and minus this one. And minus that one. So that gives us 0 equals minus 1.783 times 10 to the 4th for the numbers. And then we'll combine these T sub F factors. There are only 2 of them. So this one plus that one. And I get 3.238 plus 3.238 times 10 squared TF. So if we move this one to the other side, it makes it positive, and then divide by this one, we should get the final temperature. Yep. 55.1 TF equals 55.1 degrees C. Okay. That's a lot of work to get that one little answer. But extracting the information into this form, I think, simplifies it. Plus, understanding what this means here. Right? You're going to get, eventually, you're going to work backwards the other way. You're going to find the heat that's produced by the reaction and then ratio it to the moles of your material. So instead of sodium hydroxide, you'll have sodium carbonate, and sodium bicarbonate and water. So when you work out those problems, this term right here is going to be joules, just joules for the reaction. That's what you're going to solve for those three experiments. And then for each one of them, you're going to ratio it to the moles of water, sodium carbonate, sodium bicarbonate. Okay? And that's after you determine your calorimeter constant. Now, I hope you have better luck than we did yesterday in Beckley, because we had numbers all over the place for every group. And I even ran the calorimeter constant myself, independent from the group. And mine came out massively off from that. So we'll see. Any questions on how to do the calorimeter constant? Okay, still got, yeah, that's water topping up.